Welcome everyone. It's a pleasure to have Sheshadri here. He's visiting us from Princeton, and his advisor is Bernard Shizal, is that right? Yeah. And today the talk that he's going to give us is on learning, online learning, and adaptive frameworks for that. Yeah. So thanks a lot.
Yeah. Thank you very much. So please, needless to say, stop me in the middle if you have any questions. It'd be better to have questions in the middle rather than at the end. So yeah, this talk is titled Adaptive Algorithms for Online Decision Problems, and this is joint work with Elal Khazan from IBM Almaden. So the basic framework that, so here's a sort of motivation for this framework, and what could be more motivating than, well, making money and greed. So you've got money on one side and the stock market on the other. So every day what you decide to do is you partition your money in a certain way amongst the various stocks. So that's a portfolio. And then the stock market reveals its numbers, reveals the payoffs or the losses on the various stocks. And based on that, let's say there's some sort of a loss that you have to pay. So the loss is G1. So this happens in the first day. So the next day what you decide to do is rebalance things and construct a new portfolio. And again, the stock market then reveals its values and you have a payoff G2. And this basically continues every day. So the whole game is you do something, and then there's some agent that the environment is provided. So you always make the decision before the environment or the adversary makes a decision. And usually I should just say that we assume that this environment could be adversarial. So just to put this in more sort of concrete framework, suppose this is some convex body in some d-dimensional space. In every round, you choose a point from this convex domain. So this sort of represents choosing a particular portfolio. And the adversary then chooses some function. And what you have to pay is the function evaluated at that point. And in the next round, you choose another point. And then the adversary now chooses another function, f2. You pay f2 x2, so on and so forth. So the basic idea is this is going to come from some predetermined family of functions. So this sort of represents the stock market, for example. And this represents your portfolios. So in every round, the cute BSD devil who represents an adversary is playing some function. And it could be completely adversarial. It could actually depend on what we've played so far. And finally, what we pay is just the sum of losses. And our aim is to minimize this quantity. So note that the set of functions comes from some predetermined set of functions. And depending on the setting, it'll be a different set of functions. And this is some convex domain that sort of represents our options. And the total loss is simply summation of ftxt. And the main thing is that the adversary can choose anything, can be all-powerful, can actually depend on whatever our queries are. So this is the framework. Is this clear? So something that people might be more familiar with is known as the expert setting, where what you have is you have n experts, and the experts are basically predicting some phenomena. So in each round, what we do is we select a certain expert and say, we are going to predict what that expert predicts. Then a loss function is revealed, and we pay the loss of that expert on this function. And again, so this is adversarial. And in the end, we just pay the total sum of losses, and our aim is to minimize that. And so this would be the sort of expression for the loss of our algorithm. And the usual way in which, in the online learning setting, in which we measure performance is known as regret. So let's say this process continued for t days. We've accumulated some loss. And now let's just now we're going to construct some sort of a benchmark against which we want to perform well. So take the t functions and compute this point x star, which is basically known as the fixed optimum in hindsight. It's just sum up all the functions and find the minimum. So in some sense, it's saying that if you were constrained to play the same point every day, then this is the point that you would play. And note that our loss was simply the summation of ft xt, where xt is the point that we played in the tth round. Regret is the difference between ft xt and summation of ft x star. So simply this point evaluated on all those functions summed up. Note that x star is the minima for this. So this is a very standard notion of performance. Basically, it says that we perform as good if we can minimize this quantity. It says that we sort of perform as good as the fixed point, any fixed point in hindsight. So you can think of this as an expert setting. Suppose each point was an expert. If you can minimize this, you're sort of comparing against the loss of the best expert. And this convex body represents some continuum of experts. And the online learning problem is to basically design efficient algorithms that attain low regret for these scenarios. So any questions? I hope this framework is clear. I'll give a more concrete example describing all of this. But yes?
So the regret can be negative.
The regret can be negative because we are allowed to move. So I mean, sort of philosophically, what it's saying is that this is no movement but full knowledge of the future. Can we, with movement, compare with that without knowledge of the future? So just to put it more mathematically, so that's summation of ftxt, summation ft star. And the game is usually to get sublinear regret. So capital T represents the total number of time steps. And one thing I'll just mention is usually we assume that these functions are bounded, just say between 0 and 1. So why do we want this? Well, if you just divide this by t, that's the average regret, you'll see that as t tends to infinity, the average regret tends to 0. So what that says is our average loss is comparative with the sort of best fixed loss. And so in some sense, this represents some sort of convergence rate. How fast do we converge to sort of the optimal loss, optimal fixed loss? And note that obviously we cannot compare with the best sequence of points because we don't have knowledge of the future. So the best sequence of points can be much, much better. And that's why there's this notion of regret is defined to see if we can at least get this performance guarantee. So a sort of general paradigm or class of algorithms that works pretty well for regret minimization is called follow the leader. So in follow the leader, what you do is you look at f1, f2 up to ft minus 1. At this point, you have to play xt. You've seen the t minus 1 days, and you play the next point. And what you do is you compute x star t minus 1, which is just the minima of the sum of those functions, just the optimum in hindsight just for this section. And since you know these functions, you can compute that. And these are all, so in the case of portfolio management, these are all convex functions. So it usually ends up computing some sort of convex program. And you just output this as xt. So it says that you just find the leader for whatever you've seen so far and just play that in the next round.
In this way of presenting these methods, you assume you have the whole function.
Yes, yes.
Which could be in some of the settings I've seen where
right.
you just have the loss. But you don't have the function.
Right, that's the Bandit setting as it's known. So, so the main purpose of this talk is to define sort of a stronger notion of performance than regret. And what we're going to do is we're going to give algorithms for that much stronger notion of performance. But it seems crucial that we actually need to know the function there. And it would be interesting to see for that notion of performance if we can actually get anything in the Bandit setting. Yeah. And of course, so xt is just the minimum in hindsight for the first t minus 1, and you play that to the function ft. And what was shown was for the problem of portfolio management, which I'll define in more rigor later, but it's sort of some kind of modeling of the stock market. And for actually a certain class of loss functions, you can get log t regret. And this is extremely rapid convergence because the per round convergence is basically log t divided by t. So this is extremely rapid convergence to the optimum.
However, it wouldn't do as well in an adversarial setting because...
You mean this regret?
No, the follow the leader algorithm, wouldn't it?
What do you mean by the adversary?
So even the one who's defining the next function, the ft, he has the knowledge of f1 through ft minus 1.
Yes.
And so he could construct a function ft now.
Right.
That
it's
would
totally
result in
different
a large
from that.
loss.
Yes, but the thing is, our aim here is to minimize regret. So, and the thing is, if the adversary keeps jumping around a lot, then the optimum in hindsight goes up. And since we're trying to compare with that, we can also compare with that. So so the whole game here is even though the functions are being generated by an adversarial agent, we can still minimize regret. So it's sort of like the best of both worlds, saying that if the adversary was being very benign, then we could actually make our losses extremely small. And for the more general setting, and I'll describe these problems for something known as online shortest path, in which the only assumption usually made is that these functions are just bounded and convex. That's all you know. You get O of root t regret, which is, again, it's very rapid convergence, but not as rapid as that. And the interesting thing is that these regrets are actually tight. This is the best you can do. So one thing, just a small observation, is that follow the leader has some sort of convergence behavior. It's not hard to see that as t increases, xt minus the distance between xt and xt plus 1 decreases. Because suppose you're at the millionth step, you take the minima of a million functions. Now you add another function to it, which is just bounded, and you find the minima for that. That's just going to shift by a little bit. So what follow the leader does is it sort of tends to converge to a certain solution, which in our setting doesn't really seem like the right thing to do, because you have an adversarial agent. And obviously it seems to imply that as t increases, the amount you learn decreases, because you sort of gain inertia. And I'll make this more formal. But essentially, the argument we're making is that follow the leader does not adapt to the environment as well as it should. And this is not just follow the leader, but actually many, many learning algorithms, they tend to have this behavior, this convergence behavior, because they're trying to minimize regret. And therefore, they don't really seem to learn things as well as they should. And let me now give an example of what exactly I'm talking about. So let me give a concrete problem. Consider this to be just the unit ball in 2 dimensions, say. So in each round, we choose a point from this convex domain. The adversary, the cute BSD devil, chooses a point yt. So we choose xt, adversary chooses yt, we pay xt minus yt squared. In other words, one can just think of the function that's being played as x minus yt squared. And this is a sort of family of functions that the adversary is playing. So is this example clear? So it's not, if you just work out the math, you can show that the optimal hindsight happens to be the centroid. So once t points are played, the best thing to do is to play the centroid. And we want to compete with the loss of this point in regret. And so let me just show you how follow the leader works here. So you start off playing an arbitrary point x1. So adversary plays y1. So you play the average. For x2, you play the average of what you've seen so far, which is just y1. So your x2 is the same as y1. Then the adversary decides to play y2. So for x3, for the next decision you make, you just play the average of these 2 points. So you just play the midpoint. And then you get y3. You play the average of these points as x4, and so on and so forth. So as you can see, as time increases, the amount you move keeps decreasing. It actually decreases by 1 over t. And this algorithm actually gives O of log t regret. It's not very complicated, and it essentially boils down to this, that this point eventually does converge to x star, which is the centroid, and it moves very little as it goes, as time progresses. So now, let me give you a very simplified version of the square loss problem and show you why regret is not a good measure of performance. So consider square loss on the unit interval. So this is just, say, between -1 and +1. And let's say you decide to play this point x1. And the adversary is in a good mood and plays the same point. So you incur no loss whatsoever. So you have no reason to play any other point. You play x2, and the adversary also plays y2. And let's say this continues. So for the first t steps, you just play the same point. The adversary is playing the same point as well. So note that I'm actually describing follow the leader over here. So follow the leader would just do this. Now, what the adversary then decides, for the remaining t rounds, decides to play the opposite point. Say this was -half and this is +half. Now, if you're playing follow the leader, before I get there, the optimum in hindsight happens to be the centroid. So just the origin. So you start here. Follow leader is now going to play xt plus 2, which is just going to be the average of those t points and 1 point here. So it's going to move a little bit to the right. xt plus 3 is going to move a little bit more. And this is going to proceed in this way until finally the t2 plus 1 step you converge to the optimum in hindsight. So note that our total loss is actually omega of t, because for these t rounds, we're paying a constant loss in every round. And the regret is still small if you work out the math, but it doesn't capture the fact that we should actually play this and then after a while actually jump over there. I mean, it seems that the right thing for a quote-unquote learning algorithm would be to play that point, realize that something is going on over there, and then sort of jump. And as far as we know, there is no known learning algorithm that could do this until this work. So yeah, before, is any questions about this? Nope, okay. So let me now define a new measure of performance called adaptive regret. And the way it's going to work is in the following way. Let this be the time axis. So this is basically just time 1, time 2, so on and so forth. Choose any contiguous interval of time. So for example, j. And let's compute the regret of our algorithm in that interval, which means you sum up our losses in that interval, and then you take the best in hindsight for that interval, which could be very different from the best in hindsight overall. So has everyone sort of parsed this expression? This is just the regret for that interval. And let's just take the supremum over all contiguous intervals of all lengths. And let's call this the adaptive regret. And our aim is to minimize this quantity. So note that this trivially bounds the regret, because the regret is less than the adaptive regret. And what this says, it's basically the adaptive regret is the maximum regret over all intervals. And note that our algorithm has to be competitive with a different optimum for every interval. So this is a much, much stronger notion than regret. And this also captures the movement of the optimum as time progresses, because you can take any chunk of time, and if you could minimize this, then with that chunk of time, you would be competitive with the optimum in hindsight. And the game is to get an adaptive regret which is sublinear. What this means is in any interval of size little omega of the adaptive regret. So if the adaptive regret was square root t, choose any interval of size greater than square root t, and our algorithm would converge to the optimum in that interval. So obviously for very small intervals, there's no guarantee that you can give, because you can't predict the future. Because so for an interval, suppose this was root t, then this just gives, for any interval of size smaller than root t, this is a triviality, because all of these functions are just bounded between 0 and 1. But what this shows is that for larger intervals, you converge to the optimum. Furthermore, as the interval becomes larger, the convergence rate is even quicker.
Question?
Yes?
So is the soup there over, the notation's a bit unclear. The soup is not over the scalar j, which is the size of the interval. It's
No.
Intervals of length j, soup over position.
No, it's actually, okay, the soup is over all contiguous intervals.
Okay, I'm asking for a bit more precise definition of that.
Okay,
over
so
all possible starting positions of intervals of a fixed length, or over all possible intervals of all lengths?
all possible intervals of all lengths.
Isn't there a finite number of them? I mean, when do you need the soup?
I mean, yeah, you could just write the max, I guess, but it's not, yeah, it's some function of n, right, the number of intervals, yeah, you can.
So that includes the interval which spans the entire time series, and it also includes
Yes.
every interval of length 1 time step.
Yes. So suppose this quantity was bounded by, say, square root t. Then for all intervals of size less than square root t, it's a triviality. I mean, it doesn't say anything. But for larger intervals, you get convergence to the optimum. Actually, I guess I should be looking at the camera rather than. So I hope that's clear.
Yeah, thanks.
Okay.
Out of curiosity, can this be extended to subsequences?
So yes, there are. So There are definitions that actually do subsequences as well, and there have been results for that. But the results are not as strong as the results we'll give for this. Furthermore, this seems to capture basically sort of temporal locality. Yeah, so that's the but there are there are definitions that work for that take subsequences as well. Yeah. Any other questions? Right. So our game is to So we're going to give algorithms for this, which minimize this quantity. And just to give you an example in the square loss case, if you look at the interval t plus 1 to 2t, which is the latter half of time, the cost of the optimum in hindsight is 0. Our cost happens to be omega of t because we keep playing in that region. I mean, the cost of follow the leader. And therefore, the adaptive regret here is omega of t, which is terrible. So as far as we know, most all learning algorithms which work for the square loss case tend to give this extremely large regret. So an intuitive way of putting it is to basically say an evil algorithm that keeps following the devil. So whenever the devil plays at a certain point, we want to be able to jump over there. So let me just describe a few motivating scenarios for adaptive regret, and then I'll give the actual statement of formal results and a description of the techniques we use. So the first, again, we're back to money. So portfolio management. So the way portfolio management is usually modeled is in each round, you play this vector Vt of positive coordinates whose sum is 1. This is basically saying you split up your money amongst the various stocks in various percentages. And then let's just say that, I guess it makes sense these days that we're only talking about losses in this model. So there's a loss vector that comes out, and the loss vector usually says that suppose LT of 1 is 0.5. That means the value of stock 1 has gone down, is now just 0.5 of its original value, and so on and so forth. So these numbers are just, say, bounded between 1 and 0.5, say. And so actually, let me not go through the math, but the usual way this is modeled is we say the loss is then minus log of the dot product of these vectors. And I won't get into exactly why that's the case, but this sort of models the portfolio management. That is, if you were actually to compute all the money that you made, you could model it using this function. And obviously, adaptive regret makes a lot of sense here because you want to sort of track the progress of the stock market, not just be competitive with the best fixed portfolio in hindsight. So the stock market suddenly jumped at some stage. You want to be able to change reasonably quickly and move to the best portfolio. A more combinatorial problem that's it's very interesting is the online shortest path problem. So think of there being like a planted graph, and there's a source S and a sink T. And every day, what we do is choose a path from S to T. The adversary then reveals weights on these edges, and we pay the length of the path. So in this case, we'd pay 6, we'd pay 9. And although there were like many more shorter paths which we could have taken. And so here, as I mentioned, the loss is the length of PT, and P star is usually denotes the shortest path in hindsight, which is what we want to be competitive with. So after T days, we compute the shortest path in hindsight, and we want to be competitive with the loss of that. Also, implementing follow the leader here is very efficient because in each round, you basically do a shortest path computation of all the weights you've seen so far, and that gives you the new path to play. And another way of sort of looking at this problem is to think of there being an expert associated with each path, but there are, of course, exponentially many experts. And of course, the game is to choose between these experts in some efficient way. So in the framework of adaptive regret, it sort of makes sense here that suppose our algorithm started playing a certain path, or it started converging to a path, and then the adversary decided to congest that part of the graph. We like to sort of immediately be able to jump away from that. And if the congestion followed us, we want to keep sort of jumping away from wherever the congestion occurs. And so it says that adaptive regret means avoid congestion on every contiguous time interval. And this cannot be done by any follow the leader kind of approach because eventually it starts converging to a path. And then if the congestion hits that path, follow the leader will not be able to move away. nor, I mean, I guess sort of the efficient algorithms for this problem will not be able to do that. So we're going to describe an algorithm that we'll call follow the leading history. This is going to be a low adaptive regret algorithm. It's basically a bootstrapping procedure. So it takes a low regret algorithm for that situation, runs many copies of it, and then converts that into a low adaptive regret algorithm. And so the main thing is that we're actually able to do this very efficiently. So I'll describe that more formally, but the interesting thing is that if someone constructs a very efficient low regret algorithm for some scenario, that immediately implies through our results a low adaptive regret for that scenario. Any questions?
Sorry, could you repeat the last?
So the thing is, since it's a bootstrapping procedure, so if you have, so suppose someone comes up with a very efficient low regret algorithm for portfolio management, so we can just plug that into our thing just as a black box, and we get more efficient. And so yeah, now for something completely different. So for the X-concave setting, this was basically, think of the problem of square loss, for example, or even portfolio management. Standard algorithms would give a regret of log t, and they would have a running time, let's say, of r per round. R is the amount of work that they do. We have a bootstrapping procedure that gives an adaptive regret of log squared t, so we lose a log there. And our running time per round is now r log t. So we lose a log in both of those parameters. But note that this is a much, much stronger notion of performance than regret. Incidentally, we also get regret of log t. So we can ensure that as well. And for the general convex settings, so in this case, think online shortest paths. So online shortest paths, there are algorithms whose running time is r. R is basically the time to compute a shortest path in each round. And the regret is root t. We can get an adaptive regret of root t log t, and we pay a log t in the running time as well. So we'd be computing log t shortest paths in every round, but we get this much stronger performance guarantee. And the interesting thing is, here we can do a further optimization. So if we're willing to lose a little bit more in the adaptive regret, we can actually cut the running time down to r plus log t, which means in each round we're doing practically the same amount of work as that. We're just computing a shortest path again, but we get this very strong notion of convergence. So are the results clear?
Why do you call it Bandit?
Because we use some Bandit techniques over there, yeah. So, so yeah, follow the leading history is the sort of, we actually have different follow leading histories for both of these cases, but they form a sort of general, so the same structure. And here we do this, this optimization using a Bandit technique, which I'll, if I have time, I'll get to later. So any questions? Okay. So I have, what, 20 minutes, basically?
Yep.
Okay. So previous work, basically Littlestone, Warmuth, Herbster, Warmuth, and another studied this notion of what is called k-shifting optima. That is, instead of being competitive with a fixed optimum in hindsight, how are you competitive with an optimum that shifts k times? And we use techniques from there. Obviously, there are similarities. And our guarantees basically are stronger than their guarantees. They imply their guarantees. And also, they work for only the finite expert setting. We work for a sort of continuum of expert, or even in online shortest path, where there's sort of exponentially many experts. And as Aranyak had mentioned, like, are there sort of regret definitions that choose subsequences? So those are known as time selection functions. So you can give a function that selects some subsequence of time. But the results are much weaker than ours for this case. And there's been a lot of other work that we borrow on. And interestingly, we noticed that in the digital signal processing community, people got results very similar to ours, but using completely different techniques. So here's the sort of the basic overall idea. Let this be the time axis. So this is just time 1, time 2, so on and so forth. What we're going to do is construct a room of experts. And in each round, we're going to listen to whatever these experts predict and then make some decision on the basis of that. And the way this is going to work is, after time step 1, function f1 is revealed to us. We're going to construct the expert E1, who basically predicts FTL from that point, from the first location. So what this means is that at any intermediate time step, this expert simply runs follow the leader up to that time step from time 1 and predicts that point. It could be not even follow the leader, but any low regret algorithm over there. And at time step 2, function f2 is revealed. We construct this expert e2, who's doing follow leader from time step 2. And at time step 3, there's going to be follow leader from time step 3, so on and so forth. So at each time step, a new expert is entering the room, and this expert is simply a low regret algorithm from that time step. So this expert only sees what's in front, not what's behind. And what we do is we sort of combine everything, output some xt, then ft is revealed, and then of course et now walks into the room. So this is the sort of way it's working. It's a sort of expert setting, but where the experts keep increasing in each round. And so just to show you that we always have the right expert, let's go back to our bad example, where we had square loss in -1 to +1. Remember, the first t points were just that fixed, say, -half. The expert E1 just does FTL in that whole realm and just plays that point, just takes the average of all those points. So do all the others, because you could take the average of 1 to t, or 2 to t, or 3 to t, and you get the same point. But now let's look at what happens after the t+1 point is presented. This expert is going to take the average of 1 to t and the t+1 point, so it's going to move a little bit. This expert is going to take the average from 2 to t and then the t+1, so shifts a little bit, is actually moving a little bit more. And so on and so forth, but all of the experts here, all of the first t experts, keep playing something over that, at least for the first point, for the t+1 point. Note that, let's choose the expert ft+1, et+1, the t+1th expert. Now this guy is going to play this point throughout t+1 to 2t, because he just takes the average of whatever he sees from time t+1, so he sees everything in front, so he plays that. So I hope I've convinced you that at least in this simple example, there's always some expert that you can listen to. I mean, we have a lot of noise, but there is some expert who's telling you the right thing. And if this point were to shift, then there would be another expert that you could be listening to. So now the question is, how do you choose from these experts? So you have these t experts, and you want to choose from them. Standard approach is to do a multiplicative weight approach, which is to say that you assign a weight to each expert. This is a probability distribution on the experts, and you just choose according to that distribution in each step. And then once the tth function is revealed, you do some update on this weight. So if the loss of the ith expert on the tth step is large, you penalize him very heavily. So you bring down his probability. And this is and then you renormalize to get a probability distribution. This is a sort of very standard approach for choosing amongst experts. And so this kind of approach usually says that you will be competitive with the best expert in hindsight, but that here doesn't really make a lot of sense. So what we're going to do is a slight twist to this. So remember that after t steps, you had t experts, and then at the before t step, you have the first t-1 experts. Once ft is revealed, this new expert walks into the room. So how do you deal with this new expert? What weight do you assign to this new guy? So we have weights w1 and wt-1. Those are the t-1 experts. Now expert et enters. What we're going to do is simply do your multiplicative weights on those experts, and you get some weights. To the new guy, give him a head start of 1 over t. So you give him this little boost, and then you sort of bring down everyone else so that it's still a probability distribution. And basically, if what we show is that this head start is enough. And what I mean by that is consider any contiguous interval of time j. Let's take the expert ei, who corresponds to the first time step in that. We can prove, and I'm not going to prove it, but that's the sort of main technical meat, that the loss of our algorithm in that interval is less than the loss of this expert in that interval plus, say, an O of log t. So let's say we're in the square loss case. So we're going to pay an additional O of log t, but we get this kind of a thing. And remember that ei is actually a follow the leader. So the loss of EI in that interval is less than the fixed optimum of that interval plus an additional O of log t. So you just sort of put it together, and what you get is that the loss of our algorithm is less than fixed op plus log t. So our regret in that interval is O of log t. And let me not go through the math here. So the thing is, using this, you get an adaptive regret of O of log t. Problem is, you're using too many experts. So it's a highly inefficient algorithm because you need t experts in the worst case. So the question is, how do we actually cut down that running time? And that's where we use this interesting streaming trick. So let me first show you the best animation that I've got. So okay, think of all the experts lined up over there, and we're sort of streaming through the experts. So there's going to be a working set of experts who we're listening to. Before, it happened to be all the experts that you've seen so far. Now it's actually just going to be some subset of them. So some experts are not going to be in this set. And now, for the next cool animation, so we move from time step t to t plus 1. We decide to remove an expert. So it's like this expert is killed, basically. Once this expert leaves, he can never come back into the room. So we remove him, and we might decide to add the present expert that we see. So you see that, the working set now becomes extremely dynamic. There are people, every step there's somebody coming in, there are people leaving, and it keeps changing. And this is a little subtle, but because we define adaptive regret the way we define it, we're able to use streaming techniques, and it seems so natural here, because once in a streaming model, once you throw away something that you remember, that's it, you've lost it forever. So streaming techniques seem very, very relevant over here. So let me now just give you a short description of what is the working set at time t. So the working set is simply a set of experts you've seen so far, a subset of experts. So it's just a subset of indices from 1 to t. And here are the three key properties. So st plus 1, which is the working set at t plus 1, minus st is only t plus 1. What this means is that at t plus 1, the only thing you can add is t plus 1. And you can say, let's say that we always add the expert that we see. So that's basically what this says. And the second says that essentially the set is small, so it's O of log t. The third, well spread out, what that means is that it's sort of well spread out in a logarithmic scale. More precisely, suppose we're at time t, so let's take st. Take any interval, any contiguous interval, whose right endpoint is t. So any interval that looks like that purple thing. Take the midpoint of that, and there's always going to be some expert who's in the previous half. So you take any interval whose right endpoint is t, take the previous half of that, and we're always going to have an expert in that interval for any such purple thing. So it basically ends up looking like this. Think of there being one at distance 2, 4, 8, 16, so on and so forth, all powers of 2. And so here's the interesting thing. The definition of the working set is completely combinatorial. You would think that the most natural thing to do is to throw away experts who are not performing properly. But that's actually not what we do. That's not what we do. We just throw, according to this rule, some sort of combinatorial rule which has nothing to do with the weights. So I won't get into actually how this is maintained, but there are very elegant deterministic constructions that gives you a rule that from st, throw these people out to get st plus 1. So we can maintain these properties. And once we maintain that, what we can actually show is that suppose you take interval st, take the previous half of the interval. So there's some expert et1 in st. That's just by the properties of st. And what we can show is actually, if you take that interval j1, note that that expert sort of was born entered the room at that step and stayed throughout the whole thing, because he never got thrown out. And because of that, you can show that the loss of our algorithm in that interval is less than the loss of that expert plus O of log t, because that expert survived that whole interval. And you just sort of expand it out, and what you get is that's less than the minimum loss, fixed loss in that interval plus O of log t. And then what you can do is you can go from S to T1 and just repeat this again. So what you end up with is an expert in the previous half of ST1, and this guy sort of survived that whole interval J2. So our algorithm will be comparative with that expert there plus an O of log t, and so on and so forth. You add it up, and what you get is that the loss of our algorithm is less than the minimum loss in the whole interval plus log squared t. So what we're doing is we're taking the interval we're interested in and breaking it up into sort of logarithmically many pieces. In each piece, there's some expert who survives the whole piece, so we're comparative with that expert. And that's the basic idea. So we pay the extra log because of this splitting up. Is this clear, roughly? So we can actually get log squared t adaptive regret with sort of log t copies of the original algorithm. And the same works for online shortest path as well. The math looks different, but we get like we get O tilde of root t regret with log t copies.
Sorry, why do you need to split each interval? Why not just take the earliest expert of the interval and he's doing well throughout the interval?
So, I mean, if you want to maintain this log t kind of thing, the earliest expert will probably leave out some chunk of the interval.
Some half, less than half.
Yeah, less than half. So that's essentially what's going on. I mean, the earliest expert will probably not be the first point of that interval.
Yeah.
It'll be something who misses that.
Yeah.
So you have no guarantee on that. So for then you have to analyze that part.
Can you go back to the previous slide? So the way in which you maintain the expert is sort of in a roughly exponential increasing way from your right hand.
Right.
How do you also guarantee that the intervals that are to your left are covered? I mean, they have the same property. I thought it only held for intervals which start from the right.
Right, you're right. But now let's shift the picture to time step t1.
Okay.
And then this property holds from there.
Okay.
Because when we want to analyze the losses from t1 to t, then we look at then we look at ourselves at t1.
Oh, I see.
When to analyze the time what happens from t2 to t1, then we move to t1.
Okay, I see.
So we're actually sort of
Okay. So you don't have the best expert or rather, okay. At T you don't have the best set of experts from S to T1.
No, you don't.
You dropped him.
You drop them.
Okay.
But you have the best expert from T1 to T.
I see. Okay, got it.
I mean, the thing is, essentially at any time step, if you look at some expert, then you have, that expert survived from when he came in to the point that you have.
Makes sense.
As long as that thing is more than half of the thing,
Right.
recursively, you just keep splitting it up.
Okay.
So it's a sort of cute streaming trick, basically,
Right.
essentially. And yeah, maybe I'll just, I have around 5 minutes or so, right, essentially. So yeah, I'll just go through this a little quickly. So for online shortest paths, you're basically computing log t shortest path computations in each round. And the interesting thing is you can cut this down to just a single shortest path computation. So there are actually going to be O of log t copies of the algorithm, but we're not going to sort of use all of them in each round. And this works for general convex functions. This ends up giving an extra additive regret of root t. And that's why it's not good for portfolio management or for square loss, because this is too much for those scenarios. And the basic idea, the way it works is, think of the working set. These are a bunch of experts, each predicting a certain path. Usually you choose some expert and you basically play the path of this expert, and then the edge weights are revealed. Once the edge weights are revealed, you have to do this weight update, this multiplicative weight update. And for that, you actually need to compute the weight of all of the other experts as well. So you need to sort of evaluate, you need to compute the shortest path that all of these guys are predicting as well. And that gives you the log t shortest paths. So what we're going to do is we're just going to compute the shortest path that expert predicts. We're just going to do FTL for that interval, that expert. And we're going to imagine that the payoff is actually only revealed to that given expert, which is sort of what you were talking about, like a bandit setting. So even though that's really not the case here, we're just going to imagine that that's what happened. And this is exactly what is known as the bandit setting, in which you only reveal the loss of your chosen expert. And the interesting thing here is it's a really amazing thing of ours, Sazabianchi, Freund, and Shapire, that if you have k experts, you can get regret of root kt, even though you don't even know what the other experts are getting. And here, because of our expert reduction, we only have log t experts in each step. Although these experts keep changing in each round, we only have log t. And you push the math through, what we can get is actually that our regret is also going to be this O tilde of root t. And this is through only one shortest path computation. So note that the Bandit techniques are used for reducing the time. It's not, we really are not in that setting. And so let me just, so just to summarize, what we defined was this notion of adaptive regret. It's a generalization of regret that captures sort of moving solutions. And it means that we converge to a fixed optimum in every interval of sufficiently large size. And it's a bootstrapping procedure that converts low regret into low adaptive regret. And the interesting thing is, well, if you talk to people who actually run these portfolio management algorithms, one question they'll always ask is, how much of the history should you remember to get a good algorithm? And what we're doing is, we're sort of maintaining all histories together in some efficient way. So it's sort of dealing with the question of how much history needs to be remembered. And so just to end, further directions, I think the first thing that should be looked at is whether these sort of streaming or sublinear ideas can be used to get efficient learning algorithms. And it seems like something that people have not explored before. And now think of the following scenario where you want to have a learning setting where you have a cost of movement. So it makes a lot of sense in something like portfolio management. The moment you change your portfolio, you pay some cost for that. And now it's a completely like an online algorithms problem, which is you want to be competitive not with the best point or the best moving point, but rather with the best strategy overall. So can we use these techniques to get some kind of competitive ratio bound for those settings, where you induce a cost of changing your solution from one to another? And it seems like a really interesting thing to do, and we're actually we're trying to work on this. But I mean, the main thing that I want to say at the end is the most important thing here is not the fact that we got some adaptive regret bound, but rather that we're using sort of some bunch of techniques to get efficient algorithms to capture moving solutions. And this seems like something that has a lot of use in many other places. So it'd be nice to see where else we can use these kind of things. And with that, I'll just end the talk.